Honors Pre-Calculus, I would like to welcome you to a happy e-learning day. We are talking about roses and lemniscates, and your homework will be a Math Excel on roses and lemniscates. First, we're going to recap roses from yesterday. R equals a cosine n theta and R equals a sine of n theta are the two formulas or equations of polar graphs that produce roses. I have graphed r equals 4 cosine 2 theta and r equals 4 sine 2 theta to illustrate a couple of things that we learned. Roses have rotational symmetry, so what that means is you see the exact same petal if you rotate a certain amount, and that rotation is every 2 pi divided by the number of petals. So in this case, we learned yesterday that if we have 2 theta on the inside, we would have 4 petals, because when we have this situation with 2 on the inside, we multiply it by 2 and get 4 petals. So what we would do is we would take 2 pi divided by the number of petals, and pi over 2 is how much we rotate from one petal to the next. All the way around, we end up with 4 petals, and then we're back where we started. Cosine roses always have at least one petal on a horizontal axis. So the horizontal axis would be at either of these purple points where it starts. The polar axis would maximize the rows since sine of or cosine of 0 is 1. However, since sine of 0 is 0, sine roses don't have any petals on the horizontal axis, because the polar axis or horizontal axis would minimize the rows. So in order to find where this value would be, the first rose petal on a sine graph, you would determine what theta value would go into your sine of n theta to make it equal to 1. This occurs at pi over 2. So if I divide both sides by n, I get theta equals pi over 2n. So in this case, since n is 2, pi over 2n would be at pi over 4, and that is where this petal starts. So we're going to graph each of these roses defined below. R equals 5 sine 4 theta. I know that we learned yesterday that if I have an even number on the inside of a rose graph, I end up with 2 times that number of petals. So I have 8 petals. And if I want to figure out where I start on a sine graph, since sine graphs do not start on the horizontal axis, I have to figure out where this would equal pi over 2. So 4 theta equals pi over 2 at pi over 8. So I start at pi over 8. I also have the situation where if I want to figure out how far I go, I end up taking 2 pi and I divide it by the number of petals that I have. So I have rotational symmetry of pi over 4. Likewise for this one, and of course my r was 5, so I put the dot on the wrong spot. 1, 2, 3, 4, 5. If I have 2 sine of 6 theta, since this is even, I know I have 12 petals because 2 times 6 is 12. I will start at pi over 12, since 6 theta has to equal pi halves for this to be maximized. So I'll start at pi over 12, and 2 pi divided by the number of petals is pi over 6. That tells me how much I have to move to get to the next petal for my rotational symmetry. And so if I take all of that information and then I graph these things, this is what I end up with. What is different about these roses? Well, what we see is that these have odd numbers on the inside. And so when you have odd numbers on the inside, there's something that's a little different. The number of petals on the graph is going to be equal to n instead of equal to 2 times n. So when we had an even number on the inside, we multiplied that by 2 to get the number of petals. When we have an odd number on the inside, the number of petals is actually equal to n. And the reason for that is that when we have an odd number on the inside, once we get to pi for theta, then what ends up happening is I end up starting to get negative values for r, and it starts repeating the exact same graph that I did. So for example, if I plug in theta, or if I plug in pi for theta, I then have cosine of 3 pi, which then starts giving me negative values that I wasn't necessarily expecting when I had an even number here. So when I plugged in pi here, I had 2 pi, which gave me another positive value. So it essentially halves the period of the graph. And so what we know is that cosine graphs will start on the horizontal axis. So if I substitute in 0, I would end up with cosine being 1, so r equals 2. So 2 comma 0 is my first one. Then since I know I have 3 petals in this graph, I would take 2 pi divided by 3, and that tells me my rotational symmetry. So I would end up with another point at 2 pi over 3 and another point at 4 pi over 3. I would end up with 3 petals like that on my graph. And we'll see it when I delete it in a second. So you end up with 3 petals, and 2 pi over 3 is the rotational symmetry. For cosine of 5 theta, 3 cosine of 5 theta, once again, when I plug in 0, this is maximized. So I would have a point here. I have 5 petals, and my rotational symmetry is 2 pi over 5. And so what you see when all of this is deleted is that you end up with 3 petals, 2 pi over 3 is our rotational symmetry, 5 petals, 2 pi over 5 is our rotational symmetry. Now what about sine graphs? Well, when I have sine graphs, what ends up happening is if I have an odd number on the inside, this will still be 3 petals over here. This will be 5 petals. So the odd number gives me n petals. However, I need to start at a non-horizontal axis value, because if I plugged in 0, I would not end up with a value that would make this work out very nice. If I plugged in 0, I would get 0, so it would start at the pole. So I need 3 theta to equal pi over 2, which means theta is pi over 6 is my first value. So theta equals pi over 6. And then what is my rotational symmetry? So I rotate and get a new value. Since I have 3 petals, I need to rotate every 2 pi over 3. So if I start at pi over 6, and I add 2 pi over 3, I get to 5 pi over 6. That would be over here. Then if I add another 2 pi over 3, I get to 3 pi over 2. So my 3 petals should be something that look like that. For sine of 5 theta, I have 5 petals. I need 5 theta to equal pi over 2 for my first value to be figured out for my rose petal. So that would be at pi tenths. So that would be at radius of 4 and pi tenths. That's going to be down here somewhere. And then how much do I rotate? I rotate 2 pi over the number of petals. So that'd be 2 pi over 5. And if I look at these two things, what I end up with is I end up with exactly what we talked about. Starts at pi over 6, goes to 5 pi over 6, 3 pi over 2. And then this 4 sine of 5 theta starts at pi tenths. And then I add 2 pi over 5. And so I end up with 5 of these. Now notice the sign with an odd number, I always ended up with something on the vertical axis. So I ended up with something here on the vertical axis. For the cosine graphs, I ended up with something on the horizontal axis every time. So here is a chart that goes over all of the things that we know about r equals a sine n theta and r equals a cosine of n theta. And I'm not going to spend a whole lot of time on it. You can pause the video and write it down. So I don't want the video to be needlessly long, but just make sure that you note a couple things. When n is even, the period of the polar graph is 2 pi. And when n is odd, the period of the graph is pi. So it just cycles through the whole thing faster and then starts repeating itself faster. Notice that sine graphs have petals starting at pi over 2n because we need the interior of this to equal pi over 2 for a petal to start. And then the angle between the petals is different based on whether it's even or odd because the number of petals is different. So because the number of petals differs, the angle between the petals differs for even and odd values. The symmetry, we already talked about the rotational symmetry, but the line symmetry or reflection symmetry, when n is even, it reflects over both axes. When n is odd, sine graphs reflect over the vertical axis, and cosine graphs reflect over the horizontal axis. Now let's talk about Lemniscates. So we want to graph r squared equals 4 cosine 2 theta. So we'll start by graphing y equals 4 cosine 2 theta, which we already did. And then what we will do is we will move to Desmos, and we will graph both of these at the same time. So I'm going to plot out the rectangular graph and the polar graph. Now notice that with the polar graph, I took the square root in order to make Desmos make it work. So notice that the rectangular graph starts its cosine descent down, and the polar graph starts at a big number and then moves back to the pole once the rectangular graph gets to 0. Now what you notice is that while this is negative, r squared is not doing anything. It's pausing. So that's kind of crazy, right? This thing kind of looks like a sideways infinity. Well, not a sideways infinity, a regular infinity. But what's happening is because we have something that's squared, if we end up graphing, if we take the square root, it ends up only working about half the time. Anytime this is negative, it pauses. It doesn't work. So what if we took the negative values? notice it still pauses when I have a negative r, and then it still works while I have a positive r. So it doesn't really matter whether I use the positive or the negative when I take the square root. I still end up with the exact same value. So if I graph this, the lemniscate ends up looking something like this when I'm all done. It looks like an infinity, essentially. So what's happening in the rectangular graph when the lemniscate is pausing? Well, that is the case when I have r less than 0. So let's graph these two things really fast. So if I have r squared equals 9 sine of 2 theta, and r squared equals 16 cosine of 2 theta, let's just think about what happens. Let's plug in some numbers. So if I plug in theta equals 0, I would get 0. If I plug in theta equals pi over 4, this would be maximized, right? So I'd end up with r squared equals 9 sine of, if theta is pi over 4, I get pi over 2. So r squared would be 9, and r would be plus or minus 3, essentially, right? So what I end up with is when I have theta equals pi over 4, I end up with a maximum value at 3. And since it's plus or minus, it goes to both sides. And so what I end up with is something that looks very similar to the cosine graph that we drew, except it's sideways. And if I graphed this one, it would be a very similar case, because if theta is 0, then this is maximized. R would equal plus or minus 4. So I end up with something that looks like that. So I end up with this situation with the sine and this situation with the cosine. So let's explain the difference in the axis of symmetry. The axis of symmetry, if we have a sine with this lemniscate, is going to be at theta equals pi over 4. And for cosine, it's going to be at theta equals 0. If you want it in rectangular form, it would be the line y equals x for sine. For cosine, it would be the line y equals 0. And that's lemniscates and roses.